Hi, good evening everyone. So let's start today's class. As usual, I will first recall whatever we learned in the previous class. So basically, we in the previous two classes we are dealing with Nash equilibrium, and in the previous two classes we have learn what does mean by the equilibrium concept or solution concept when two rational player, and by rational means I am saying that when two VNM rational players are playing a game, what can be what can game theory prescribe or predict such that the solution will be consistent with their behavior or with their preferences. And the equilibrium means we try to find such a strategy for each player, such that in that strategy no player has any incentive to deviate from that strategy unilaterally when others stick to their strategy to gain in terms of utility or payoff. So that means Nash equilibrium in a sense is a steady state in that sense. So if they are in the Nash equilibrium, they will be in the Nash equilibrium. No player don't want to change their strategy. And we have seen we have calculated and seen many Nash equilibrium, as well pure Nash equilibrium as well as mixed Nash equilibrium for many two player two strategy games. And we have seen the base response function, and how one can find the Nash equilibrium by using base response function. And the base response means nothing but finding the set of strategy in where if you know the all other opponents strategy, then base response function is nothing but the set of those strategies. If one adapt those strategy given the other player strategy, it will maximize his payoff, or maximize his utility or payoff. So mixed Nash equilibrium or any Nash equilibrium is nothing but the base response to each other strategies. And we have seen using that property, we have seen graphically as well as by numerically we have solved, or not numerically, graphically we have solved and see how we can determine the Nash equilibrium. Particularly in case of mixed Nash equilibrium, we have seen a property that mixed Nash equilibrium is always a non-strict Nash equilibrium. That means the equality holds in this case. If I go back to the Nash equilibrium definition, if I go back to the Nash equilibrium definition, so here a equality sign is there. So if all, so this means, so you can see that if equality sign holds, then also Nash equilibrium can a strategy can be qualified as Nash equilibrium. And we have seen particularly for mixed Nash equilibrium, all this equality holds, and all the mixed Nash equilibrium are non-strict equilibrium. And using that property, we can calculate the mixed Nash equilibrium by means we can calculate the other players strategy by equating the expected utility of the available action to player I. So suppose for two player two games, if I go back to any example, so for here suppose by equating its two equating player one's expected utility for head and tail in matching penny games, that is 2q minus 1 equal to this is, yeah, 2q minus 1 equal to 1 minus 2q. If you equal it, if you equal it, 2q minus 1 equal to 1 minus 2q, you will get 4q equal to 2. That means q equal to half, and we know that q equal to half is the Nash equilibrium strategy of player 2. So by equating the expected utility of player 1, we will get the Nash equilibrium of player 2, the strategy, and also by equating, similarly by equating the player 2's expected utility for head tail, will get the value of p, which is nothing but the strategy corresponding, player 1 strategy corresponding to the Nash equilibrium. So that's how one can calculate the Nash equilibrium. However, in so to calculate the Nash equilibrium, you have to follow the axioms of VNM expected utility. However, in reality, you always find that the VNM utility individuals always does not follow the VNM utility. Particularly, the axioms of continuity has to be held in a lottery for existing expected utility. But in real world, these with real humans and real agents, you always find that this axiom does not hold, and there is a experiment by Selton and Chimura in a completely mixed game. Completely mixed game means like matching penny games where no pure strategy Nash equilibrium present, only mixed strategy Nash equilibrium present. That is called the mix. That is called pure or completely mixed game, or it is called only completely mixed game. Completely mixed game, no pure Nash, only mixed Nash. An example is matching pennies. So for such games, Selden and Chimura, by experiment with real human beings, find that they always the Nash equilibrium the prediction of Nash equilibrium does not matches with this kind of completely mixed game, which suggests that the individual behavior does not compile, or does not means individual is does not model, means cannot be modeled by the cannot be modeled by the VNM utility axioms, VNM expected utility theory. Why? If it follows the VNM expected utility theory, then we can the uh, only outcome possible was the in the mixed Nash game, only outcome possible is the Nash equilibrium. However, they are finding another thing, at their behavior, humans behavior, real humans behavior, and it is published in by Selton and Shimura in 19 I think in 2007. They published the paper where you can find that human behavior closely matches with procedural rationality. Procedural rationality rather than VNM rationality. And what is this procedural rationality? That we have learned in when we learned in the very beginning of this course, when we are talking about the decision making under uncertainty. We first learn about the concept of VNM utility, then we have gone through this concept procedural rationality. So let me revisit that again. Yes, this is the this is the this is the lecture where we have discussed about the concept of procedural rationality. So we have seen that the humans preferences are bounded rational and particularly procedural rational, and the Osborne and Rubinstein, how the concept of procedural rationality is bounded rationality is captured by the procedural rationality, and it actually captures the stochastic preferences of human beings rather than deterministic VNM rational preferences. And what does procedural rationality means? So an example of procedural rationality means, suppose you have a lottery. So um, let me again clear a page here. Let me write it. The chapter name is sampling equilibrium. Okay, so first, what does mean by procedural rationality? So it is the same thing that we have learned in the beginning of these courses. Procedural rationality. So suppose, procedural rationality is a way where the uh, axiom corresponding to the continuity axiom does not hold of expected utility theory. So the natural question is, what should be the way of representing an uncertain decision makings in terms of utility? And here we will see that it will using a stochastic utility to represent uncertain situations. So suppose there is a lottery. So lottery is, suppose you will get prize AI with probability x, or let me write it with probability alpha 1, and with probability alpha 2 it will get a prize. So there is a lottery, whose prizes are A1 A2 with probability alpha 1 and alpha 2. Alpha 2 is nothing but 1 minus alpha 1. Now how a procedural rational agents evaluate this lottery? So suppose there is two lotteries are there. Lottery 1 is there and lottery 2 is there. Suppose it will get same probability with A3 and with this probability alpha 4. Now in case of VNM utility, it will the utility of lottery 1 will be nothing but alpha 1 into utility of A1 plus alpha 2 into utility of A2, alpha 2 into utility of A2, and utility of L2 is alpha 1 of utility alpha 3 plus alpha 2. Now a VNM rational agent will compare between these utility. It will choose L1 over L2 if and only if U L1 is greater than U L2. Now let's see the case of, this is the case of VNM rational agent. Now the case of procedural rational agent. Procedural rational. In this case, so what the procedural rational agent will evaluate the lottery. So either he sample each lottery once, or this sample can happen also that the individual can ask her friend what he got, what her friend's experience about the lottery 1 and lottery 2, and the friend can tell her that with lottery, when she brought lottery 1, she got, his friend, she got A1, and when she brought lottery 2, he got A3. So first, this procedural agent sample each of our lottery once to determine the utility, or in terms of the consequence to the consequence of lotteries. So first, these consequence can happen. So whatever I am telling, so this consequence can happen. She might not individually go and sample each lotteries. It also be a case that she asks her friend who has experience in these lotteries, and that her friend tells that when I brought the ticket L1, it is friend brought when I brought the ticket L1, I get suppose U1, and when I brought the ticket, not I brought the ticket, I get A1, and when I brought the ticket A2, I get A4. Now the consequence, now he will associate the consequence A1 with lottery L1 and consequence A4 with L2 from this one sample. And if he sample the lottery independently, then might also she found that when she'll sample, and here I am using sampling 1. So when she sample each lottery independently, when he sample in L1, she realized that L1, for that sample, L1 will going to give her A1, and L2, for that particular sample, it will give the lottery L2 is going to give her A4. Now what she will do, she will choose the lottery with best consequence. So here So when in this case, in particular case, when C will change, suppose A1 is greater than A4, then when if A1 is greater than A4, in this case C will choose L1 over L2. Now as you can see in this sample, she realized A1 and L4, and it should be it is with some probability. So what is will be the probability that she realized A1 corresponding to L1 and A4 corresponding to L4? So it will be with probability alpha 1, and it will be probability 1 minus alpha 1 and alpha 2. So what will be the probability that she will consequence the action the outcome A1 with lottery L1 and A4 with lottery L2? That probability will be nothing but alpha 1 into alpha 2, that is 1 minus alpha 1. So this is the lottery. So with alpha 1 A1 or alpha 2 A4, so that means, so it is a stochastic event. So how many realization she could find in her sample? So this is only one place, only one thing. So she also might equally find that realize that with when she brought the ticket L1, it will going to give her a prize A1 with probability alpha 1, and L2 will A3 with probability again 1 minus alpha 1. Similarly, L1 is going to give her A2 with probability alpha 1, and L2 will going to give her alpha 3 with 1 minus alpha 1. So there can be 4 outcomes. A2 with probability L1 with alpha 1, and L2 is consequence is A4 with probability 1 minus alpha 1. So this should be the probability 1 minus alpha 1, 1 minus alpha 1, 1 minus. So that's how procedural rational agents who samples each her action only one times determine any actions. Now let us go to the case of a game where we can find out the what is the if agent. Now the question is, before going to the game, now we will go to, this is the decision making under uncertainty, which is a recall of previously learned concept. Now let us going to the case of game theory. Now in game theory, when two players are strategically interacting with each other, now if one individual is one individual's decision making can be modeled by this procedural rationality, then how can we how could we, or what will be the way of a solution concept? Or the question is there, the question is there in solution concept present when players are procedural rational. And solution concept means we know that we are finding a concept of equilibrium. So in equilibrium, no player wants to deviate from the equilibrium given other players strategy. So we are trying to find out such equilibrium concept. Now I am saying that yes, there is present a equilibrium concept. Yes, one can write a equilibrium concept which is known as, in this case, is, as we have learned, the Nash equilibrium for the case of the player of VNM rational individual. The equilibrium is Nash equilibrium. In this case, the equilibrium is sampling equilibrium. And this concept was first introduced by Osborne and Rubinstein in a paper published in 1998. The name of the paper was Games with procedurally rational. Yes. Now let us give the definition of this equilibrium. Suppose the player action sets are A, and here also we will, the equilibrium means a mixed strategy action profile is called sampling equilibrium if player I finds her strategy finds her strategy strategies finds her strategy strategy is the is finds her strategy is the best. Okay, finds that our action A K is based with probability sigma I star AK. So So action profile, so suppose, let me, what action profile, here I am not giving the action profile. Suppose the action profile is sigma star is such that every player's action is denoted by the sigma 1, sigma 2 star, and suppose there is n players present there. And what sigma 1 star means, it is a vector which corresponds the action, the probability, the strategy of player I. So strategy of the player I is the, what is the probability of playing the action A1, what is the probability of playing action A2. Now suppose the player 1 has mi strategy, what is the probability of a mi strategy. So this will be denoted by sigma strategy. This is the strategy, mixed strategy of layer I. Now a action profile will be called sampling equilibrium if the player finds, suppose a player I finds her action AK, suppose AK is based with probability same as with which it is playing the in the equilibrium with which it is playing the with which probability it is playing the strategy AK given the other player strategy. So what does it mean? What does the based means? So based actually means, based means nothing but, based means it finds the consequence associated with action AK is largest among her sample, where she samples each of her action once independently. So it will be clearer when we will see an example for two players to two strategy case. Let me see an example. Example of two players, two strategies game. So game is, suppose that each player has two actions A and B. Each player has two actions A and B, and the payoffs and the payoffs are given in the following matrix. matrix. So let me give you the matrix. So this is a very interesting example because we will find that we'll obviously do these things. So we'll find that the Nash equilibrium, mixed Nash equilibrium, and the sampling equilibrium is not equal here. Okay, so let me put some number. So 2 4 3 1. As we know that if the game is symmetric, so preference of both players are symmetric, so we can write by single number, because for the player 2 also the game will be same. Now suppose that the probability in equilibrium, suppose that let me wait for a moment. Let me check it. Suppose that the probability, the sampling equilibrium is, suppose that the sampling equilibrium is the accent profile. So sampling equilibrium will be, I have to, so sampling equilibrium sigma star will be, I have to assign strategies to every player. Now since the player 1 and player 2 are same, their preferences are same, and there is it is reasonable to assume that both player strategy will be same. So sigma 1 star will be equal to sigma 1 star will be same as sigma 2 star. So we can write it is by sigma. Now what is the sigma star? Sigma star is a vector which associate the probability of choosing A and probability of choosing B. So these are nothing but probability of choosing A, and this is probability of choosing B. Now since these are the probability of choosing A and B, and these are the only two events, we can write, so this should be hold that sigma star A plus sigma probability of choosing B should be equal to 1. So that means sigma star B can be represented by 1 minus sigma star A. Now for the simplicity, let us represent this sigma star A by a number alpha star. So that means one can write the strategy sigma star corresponding to, okay, so here there is a problem, so symbolical problem is there, so let me write it sigma tilde, because this sigma same, so sigma tilde here, this is sigma tilde, so this is sigma tilde, sigma tilde, sigma tilde, sigma tilde. Why I am changing the sigma tilde? Because you see the here the symbols are same, so I am not, this is a vector which contain two vectors inside itself, because this is corresponding to the all strategies of player 1, this is corresponding to all strategy of player 2, and in the symmetric game the players 2 strategy is same, so that's why it can be represented by a same vector sigma tilde star. Now this sigma tilde a sigma tilde star is nothing but the probability of choosing A and probability of choosing B, and if this is the case, then it should be the sum of these two should be 1, and this should also be whole sigma star A and sigma star B should be greater than equal to 0, and their sum should be 1. And let us write that sigma star equal to A alpha star. Then we can write the strategy is nothing but alpha star 1 minus alpha star and comma alpha star 1 minus alpha star. Now since we can represent the strategy only by a single number alpha star, the probability of choosing A, from now onwards by strategy we will mean this alpha star. Now so let me copy this game, because this game will also needed for our later discussion. So this game is required for later. So now this perfect. Okay, now we know that the action or the strategies are the sampling equilibrium is alpha star and 1 minus alpha star. If it is the sampling equilibrium, then one property it should hold. It should hold the probability. This is the probability of the sampling equilibrium. The probability of choosing any action. So when a player choose a action, suppose probability of any action, alright, suppose choosing action A or B, so probability of choosing action A, when the individual choose action A, if she procedurally rational, when she finds the action the consequence corresponding to A is best, so action choose, so that means the same as this means actually this implies the probability of finding the consequence associated the consequence associated with A is the best. And in case of equality we will this is the one, and second case we have also write that the best. And if suppose that in the sample space in the sample action consequences, so out of suppose out of sample accent consequences, n accents or q accents consequence are same, then how it will decided? So it will decided by that it will it will realize that each of these action whose consequences same is based with probability with probability 1 over q. So we will find this tie breaking rule in um, in, in the next example. I think in the next example, or I will made up an example to show it. Now let us focus in the first property of the sampling equilibrium. So why it is the equilibrium property? Because if she finds that the consequence associated with the a is based with probability same as the probability with which it is choosing the action a in the sampling equilibrium, that means she don't has to change her strategy anymore. That means she will stick with that strategy, and she don't has to deviate from that strategy. There is no incentive to deviate from the strategy, given uh, given that all other players are not changing their strategy. So let me let me calculate that what is the probability when others are choosing with probability, his opponent is choosing with the sampling equilibrium probability, that means alpha star and 1 minus alpha star. So let me calculate. So this is nothing but for the player 1. So this is player, suppose this is player 1, this is player 1, this is player 2. So for player 1, for player 1, for player 1, so his action a is nothing but a lottery with probability alpha star it will get a prize, and with probability alpha 1 minus alpha star it will getting another prize, because with alpha star opponent is playing a. So that means if she sample the a once, it can get a prize 2 with probability alpha star, or it can get a prize 4 with probability 1 minus alpha star. So for player 1, for player 1, for player 1, when she sample the action, when she sample only once the action a, it realize that it may get a prize 2 with probability alpha star, or it may get a prize 4 with probability 1 minus alpha star. And when she samples similarly, what she realize, and sample once means she may realize only one of these two outcome. She cannot realize both of these two outcome, but one can calculate with which probability she may get 2 and with which probability she may get 4. But in her sample she only get one prize out of 2. She cannot get both prize at the same time, so she may either realize 2 or may realize 4. Similarly, when she samples b, she may realize 3, either realize 3, or she may either realize 1. Now if I ask what are the consequences, um, what are the what are what means what is the sampled space of player 1s look like if he samples one and independent, with which probability the with sample space occurs. So in the sample space it may happen so when she sample A, it realize outcome 2, and when she sample B, it realize outcome 3. So 2 comma 3, and with which probability it may happen? So with which probability? Alpha star into alpha star. So because she samples independently, similarly she can realize the 2 comma 1 with probability, here with probability alpha star into with probability 1 minus alpha star. So here also it can realize the 4 comma 3 with probability 1 minus alpha star into alpha star, 1 minus alpha star into alpha star, or she may realize 4 and 1 with 1 minus alpha star into 1 minus alpha star. Now if I ask what is the probability that she realizes into so her sample space is stochastic, so she may either realize this outcome or this or this or this, and we know we can calculate what is the probability that she may realize this outcome or this outcome or this outcome, because she sampled two options independently, we assume that. Now if I ask another question, what is the probability that she realizes that her action A is best, and that is equivalent to say the consequence of A that she realized is the best. So when it will happen? So in this case it is not happening, because in this case if she realize this outcome with probability alpha star square, then in this outcome you find that the consequence of A is 2 and consequence of B is 3. Obviously consequence of 2 is lesser than consequence of B, so in this case she find that no, since A, the consequence corresponding to A is not best, consequence of B is best here. But here in this case the consequence of B is A is 2 and B is 1, so in this case the consequence associated with A is the best, and here also she find that the consequence associated with A is best, and here also she find that the consequence associated with A is best. So what is the probability that he is finding that consequence is best? That means he realizes that action is best. So with probability, if she realizes this or this or this, so that means we have to sum all the probability of these three events. So that is alpha star into 1 minus alpha star excuse me, plus 1 minus alpha star into alpha star, plus this is 1 minus alpha star square. So for the moment let me recheck it. So let me do it. Here it is, we can 1 minus alpha star, take it alpha star plus alpha star plus 1 minus alpha star we can, it is like that 1 minus alpha star into here 1 plus alpha star. So 1 minus alpha star square. Now when it will be the equilibrium? It will be equilibrium if the probability of realizing that her action A is best, and when she finds the action A is best, she will going to choose the action A. So that means with which probability, in this sense with which probability she will take the action A. So with this probability, now what is the equilibrium? Is her probability of choosing the action A is same as the realizing that action A is base. So that means there will be no incentive to change her strategy from alpha star to any other, because she will find that alpha star is the probability of choosing the action A is best. So that means if I 1 minus alpha square, if I solve this, so alpha square minus alpha minus 1 is 0. So if I 2 alpha equal to plus 1 plus minus root over b square minus 4ac by 2, so that is 1 plus minus root 5 by 2. So I think something is not correct here. I think this is not minus sign, this should be plus. So this is minus, and so this will be minus. So this is, so since the probability cannot be negative, probability has to be greater than 0. So that means alpha star has to be equal to root 5. So let me, so wait for a minute. So that means here the sampling equilibrium, the strategy corresponding to the sampling equilibrium is root 5 minus 1 by 2. So now we have calculated what is the sampling equilibrium here. So that means alpha star equal to root 5 minus 1 by 2. So this is the sampling equilibrium. This is the sampling, only sampling equilibrium. Now if I want to calculate what is the Nash equilibrium corresponding to this, so let us calculate that. So let me capture it again, so copy it again. So we will calculate the Nash equilibrium. So first we will see the mixed Nash equilibrium. Suppose, what is the mixed Nash equilibrium? Suppose the mixed Nash equilibrium is denoted by x star and 1 minus x star. So what will be the mixed Nash equilibrium? Mixed Nash equilibrium will be corresponding to the probability where, suppose this is y star 1 minus y star, and it is symmetry game, so this will be the same, so no need to write it. So we know that we can get this x star and 1 minus x star by equating the expected utility corresponding to a, what it will be, 2x 2 into x plus 4 into 1 minus x. And what is the expected utility? Utility corresponding to p, that is 3x plus 1 into 1 minus x. Now we know that how we can find the corresponding mixed Nash equilibrium if we equate these to 2x plus 4 1 minus x equal to 3x plus 1 minus x. So if I take this way, 3 1 minus x equal to x, so 3 minus 3x equal to x, so we find that 4x equal to 3, so we find that x equal to 3 by 4. So I find that the mixed Nash equilibrium is not same as sampling equilibrium. And let's see another example. See another example where equality is there, so that we can calculate. Suppose our game has two action in and r in and r. Suppose this is corresponding to 1 1, this is corresponding to 0 0, 0.5 0.5. So that means again it is a symmetric game, so no need to write this again. 0.5. Let us calculate the sampling equilibrium. So suppose that alpha star and alpha star is sampling equilibrium. Now what is the probability that the player realize that his action n is the n is base? That means the probability of finding the consequences of n is based when she samples each of her action n and r once and independently. So if she find these, so in n she find 1 and in r she find 0.5, then she will realize that her action n is n, the consequence associated with the n is based with probability alpha star square. And also find in this outcome when she samples n it find 1, and when she samples r it finds 0 with probability alpha star into 1 minus alpha star. Then also she find that action n is associated n is based. However the equality appears here when she samples r, so samples n, when she find 0.5, when she find when she sample n she may find 0.5, and when she sample r she may also find 0.5. Now how she decided the action is based or not? Since as we have discussed in this case, that out of the sample actions consequences, if q actions consequences are sum, then it is that with 1 by q probability it will find that the action is based. So that means here, since both consequences are same, it will find that with probability half these consequences n is the consequences associated n is half. So that means with which probability it may appear multi 1 minus alpha star, and in case of point 5, point 5, point 5 and 0, so in case of point 5 or 0, so point 5 and 0, here also find the accent associated with n is base. So what is the probability? Overall probability, that probability will be alpha star square plus first alpha star square plus alpha star into 1 minus alpha star plus half into 1 minus alpha star, and here plus 1 minus alpha star square. So this should be equal to the probability of choosing alpha star. The probability of finding alpha, here the accent n is base, that means the probability with which in her sample she finds that her accent ends associated with based consequence with probability alpha star. So that should be equal to this. So if I simplify this, alpha star square into, so if I alpha star plus 1 minus alpha star 1 alpha star, here half alpha star plus 1 minus alpha star, so this will be alpha star plus here 1 minus alpha star into 1 minus half, so this will be 1 minus half, oh sorry, 1 minus half alpha star. Or if I simplify more, step plus 1 minus alpha star minus half alpha star 1 minus alpha star. So this is cancelled out, so it remains 1 minus half of so let me recheck it then. Let me recheck it, because the outcome is not coming what I am expecting, so might be some issues is there. So up to this is right, so up to this is right, so maybe in this way one can think. Okay, so let me check. With probability alpha star, with probability alpha star it will get, with probability alpha, with probability, so this should be alpha star, this is alpha star, this is alpha star, this is Okay, so it might be alpha star plus alpha 2 1 minus alpha star plus half plus 1 minus 1 minus alpha stars. So it will be 1 minus alpha star square minus alpha star 1 minus alpha star minus half alpha star 1 minus alpha star. So these will be 1 because alpha star plus 1, so this is 1 minus alpha star 1, so this is 1 minus half into alpha star 1 minus alpha star. So this is the case. Okay, let me 1 minus half alpha star plus half alpha star square, so 3 by 2 alpha star. Now if I put alpha star equal to 1 here, alpha star equal to 1, we'll find that the solution of this equation is alpha star is equal to 1. So that means alpha star is equal to 1 is the sampling equilibrium, is the sampling equilibrium, and the sampling equilibrium is, that means, corresponding to a pure equilibrium, that is corresponding to the action n. And here before ending this class, I want to mention that in this game you will find that the action n is also a pure strategy Nash equilibrium, and there is a theorem associated, there is a theorem which connects these two equilibrium concept, and it says that any pure Nash is any, let me recheck it. So for two player two strategy game, we know that any pure Nash equilibrium strategy is also sampling equilibrium. So the reason is that, so to calculate the pure strategy Nash equilibrium, you don't need to use the don't have to use the axiom of continuity, only transitivity. So you don't need pure transitivity and completeness. Only these two axioms are required for pure Nash equilibrium. And for the sampling equilibrium, you also find that the sampling equilibrium, the continuity does not holds pure Nash equilibrium. For sampling equilibrium, any sampling equilibrium, mixed or pure, continuity does not hold. So continuity does not hold, however the transitivity, so only we use the property of transitivity and completeness, and out of this property the sampling equilibrium emerges. So that's why for the pure case, since in the Nash equilibrium also these two axiom, actually there is no need of using continuity axiom. Only transitivity and Nash equilibrium, transitivity and completeness emerge, generate the Nash equilibrium, or if the only two axiom holds, we can calculate the pure Nash equilibrium. And the equilibrium for a game is same for the concept of equilibrium is same for these Nash equilibrium and sampling equilibrium, because equilibrium means we are want to find a strategy where no player has any incentive to deviate. So this definition is equally true for both equilibrium concept. Only in the sampling equilibrium, the continuity, we don't use the continuity axiom, whereas for the Nash equilibrium, particularly for the pure mixed Nash equilibrium, we use the concept of continuity axiom. So that's why the you will find that the mixed Nash equilibrium generally does not equal to the different from the mixed Nash equilibrium. So Nash equilibrium generally different from the sample equilibrium that we have find in the example, the first example. However, in the second example, we find that the pure Nash equilibrium is same as the sample equilibrium. It is because of the fact that we are discussing that the only transitivity and complete out, it's only because of completeness and transitivity the pure Nash equilibrium emerges, and also pure sample to calculate the pure pure sampling, to calculate the sample equilibrium, we use only these two axioms. So that's it for today's class. Now we are at the end of this lecture series. Now in the next class we will discuss about the evolutionary game theory, and this will be the end of this class, so that this course. So that's it.